Every time you ask an AI a question, your brain fills in a detail that doesn't actually exist. It happens so quickly you probably never notice it. You type a question. A few seconds later, an answer appears. Without thinking about it, your mind imagines the model going somewhere to find that answer, almost like opening a book to the right page. It feels obvious. It also happens to be wrong. There isn't a hidden library inside modern AI. No shelf-labeled history, no drawer-marked physics, no folder containing everything it's learned about the oceans, music, or the human body. That raises a much stranger question. If nothing is stored like a book, where does the answer come from? Keep your first guess in the back of your mind. Don't change it yet. By the end of this video, you'll be able to test it against the way today's AI actually works. For years, researchers believed intelligence could be built one fact at a time. Teach the machine enough rules, feed it enough knowledge. Eventually, intelligence would emerge. On paper, it sounded reasonable. In practice, it kept breaking. Language refused to stay inside neat categories. Take the word light. It can describe brightness, it can describe weight, it can describe a color, it can even describe someone's mood. The word stays the same, the meaning shifts with the situation. That's a problem no rulebook can fully solve. Stuart Russell and Peter Norvig have long argued that one of AI's biggest challenges isn't collecting knowledge. It's representing knowledge in a way that still works when the context changes. That single idea changed the direction of artificial intelligence. Researchers stopped asking, how do we teach a machine every fact? Instead, they asked something much more interesting. What if meaning doesn't come from definitions at all? What if it comes from the companies keeping ideas? That sounds like a small shift. It wasn't. It completely changed how modern AI learns. The next breakthrough didn't happen because computers memorized more information. It happened because they stopped treating knowledge like a filing cabinet. And once that happened, something unexpected began to take shape. That unexpected shift began with a simple question. What if a machine didn't need definitions? What if it could discover meaning on its own? At first, the idea sounded almost impossible. Imagine learning a language without a dictionary. No one tells you what a word means. You simply see it over and over, surrounded by other words. Slowly, patterns emerge. A child learns language in much the same way. No one explains every word with a perfect definition. Children connect words to moments, places, emotions, and people. Over time, those connections become meaning. Modern AI doesn't learn like a child, but it does learn from patterns, only at a scale no human could match. It processes billions of words, searching for regularities that appear again and again. Ian Goodfellow, Yoshua Bengio, and Aaron Corville describe this approach as representation learning. Instead of programmers defining every concept, the network builds its own internal structure, one that's useful for making accurate predictions. That changes everything. Take the word doctor. No one tells the model that doctors work in hospitals. It notices that doctor, patient, hospital, and medicine keep appearing together. Not every time, just often enough that a pattern becomes impossible to ignore. Now multiply that process across millions of ideas. The model isn't memorizing facts. It's reshaping itself. Every prediction adjusts millions of tiny numbers. Most changes are so small they'd seem meaningless on their own. Together, they gradually reorganize the network. That's why asking, where is the idea of a doctor stored, misses the point. There isn't a single place. The idea exists because countless small adjustments now work together. Goodfellow, Bengio, and Corville emphasize that modern neural networks don't rely on isolated symbols. Concepts emerge from many interacting features spread throughout the network. That design makes the system surprisingly flexible. It doesn't just repeat what it has seen, it begins responding to things it has never seen before. Researchers call that generalization. It's one of the biggest reasons modern AI feels so different from the systems that came before it. But there's still a missing piece. We've seen how the model learns, we've seen how it organizes information, we still haven't answered the most important question. If these ideas aren't stored like files, what do they actually become inside the model? The answer isn't a sentence, it isn't a rule, it's something far more unexpected. A landscape. Imagine walking through a city you've never visited. On the first day, every street feels random. A week later, you barely need a map. The city didn't change, your understanding did. Modern AI goes through something surprisingly similar. As training continues, isolated words stop behaving like isolated words. They begin finding their place among everything else the model has learned. Researchers call this latent space. The name sounds complicated, the idea isn't. Think of it as a map, not of countries, not of streets, a map of meaning. On this map, nothing has a fixed address. Instead, every idea is positioned by its relationship to every other idea. A planet naturally settles near orbit. Ocean drifts closer to wave than keyboard. A violin belongs much nearer to an orchestra than a volcano. No engineer places those ideas there. The model does. Ian Goodfellow, Yoshua Bengio, and Aaron Corville explain that deep learning builds representations that preserve the patterns most useful for prediction. The network isn't trying to copy human knowledge. It's building a mathematical structure that makes future predictions more accurate. That's why this map matters. Distance no longer measures space. It measures similarity. Move two ideas closer together, and they begin sharing information. Separate them, and they behave more like strangers. This is where AI starts surprising even experienced researchers. The model begins recognizing patterns nobody explicitly taught it. Take countries and their capitals. Researchers found that the relationship between Paris and France resembles the relationship between Tokyo and Japan. The same thing happens with singular and plural words, present and past tense verbs, even ideas that belong to the same category. Nobody wrote those rules. They emerged from the geometry itself. Pause on that for a moment. The model isn't following a giant list of instructions. It's navigating a landscape it quietly built during training, and once a landscape exists, new paths become possible. That's why AI can often answer questions it has never seen before. It isn't searching for an exact match. It's moving through nearby ideas until a new answer begins to take shape. This is also where many people reach the same conclusion. If it can do all of that, isn't that understanding? Before you settle on an answer, here's something worth thinking about. If intelligence can emerge from geometry alone, what exactly separates calculation from comprehension? Keep your own answer in mind. In a moment, we'll test it against one of the biggest debates in artificial intelligence. Because what happens next isn't about mathematics anymore. It's about us. By now, the picture looks very different. AI isn't pulling answers from memory. It's navigating a landscape shaped by billions of tiny adjustments. That alone explains a lot. It doesn't explain the part that's hardest to ignore. Why does it sometimes feel like the model is thinking? Ask it to compare a black hole to a whirlpool. Explain quantum mechanics like you're talking to a 10-year-old. Rewrite a legal contract as a country song. Many of those exact requests never appeared in its training data, yet the answers often feel original, not copied, constructed. That's where generalization becomes the real story. Ian Goodfellow, Yoshua Bengio, and Aaron Corville explain that a well-trained network doesn't just remember examples. It learns patterns that continue working when the details change. Think about recognizing a chair. You've seen thousands of them. Wooden chairs, metal chairs, office chairs, rocking chairs. No two are identical, yet your brain rarely hesitates. You aren't memorizing every chair you've ever seen. You've learned the underlying pattern. Modern AI does something similar with language. It doesn't remember every sentence. It learns structures that can be rearranged into sentences it's never encountered before. That's why it can respond to unfamiliar questions, not because it's recalling the answer, but because it's building one. This is also where the debate begins. From the outside, that process can look remarkably human. Brian Christian points out that prediction has become so powerful that it's easy to mistake fluent language for genuine understanding. The better the prediction, the stronger that illusion becomes. But prediction and understanding aren't automatically the same thing. Imagine meeting someone who has memorized every move in a chess game. They might predict the next move with astonishing accuracy. That doesn't necessarily mean they understand why a grandmaster chose it. Now imagine someone who has studied millions of conversations. Patterns begin to emerge. Certain ideas naturally lead to others. Some questions almost always end with similar answers. Eventually, prediction becomes so refined that it feels like reasoning. From the outside, those two can look almost identical. That's where our own minds enter the story. Humans are wired to detect intention. We see faces in clouds, we hear emotion in music, we assign personalities to cars, pets, and even computers. Language amplifies that instinct. When something speaks fluently, we naturally imagine a mind behind the words. The model never asks us to make that assumption. We do it automatically. So here's the question that matters. If an AI can organize knowledge, adapt to new situations, solve unfamiliar problems, and communicate with remarkable fluency, what's still missing? Don't answer yet. Because the final piece isn't about what AI has learned, it's about the assumption we carried into this video before the first sentence was spoken. Let's go back to where we started. You asked an AI a question. Without realizing it, your mind imagined the answer already existed somewhere inside the model. A hidden memory, a quiet archive, a place waiting to be searched. Now that picture looks very different. There isn't a hidden room full of ideas. There isn't a dictionary the model flips through. There isn't even a complete answer waiting to be retrieved. Each response is built one prediction at a time. Each prediction is guided by the invisible landscape the model created during training. That's the real breakthrough. Ian Goodfellow, Yoshua Bengio, and Aaron Corville describe deep learning as discovering useful representations instead of handcrafted rules. The achievement wasn't giving machines more knowledge, it was finding a better way to organize it. Stuart Russell and Peter Norvig arrived at the same challenge from another direction. Intelligence has never depended on how many facts a system contains. It depends on how those facts connect, how they're represented, how they're used when the situation changes. Modern AI does exactly that. Not perfectly, not consciously, but remarkably well. And that's why this conversation has become so difficult. Because the better these systems become, the easier it is to mistake capability for consciousness. Brian Christian argues that this is one of the defining questions of modern AI. When a model produces language that sounds thoughtful, we're judging the result we can see. The process behind it is something else entirely. The model doesn't experience surprise, it doesn't feel curiosity, it doesn't pause to admire a sunset or remember yesterday. It transforms patterns into predictions with extraordinary precision. Whether that process should ever be called understanding is still an open question. Researchers continue to debate it, and they probably will for years. Which brings us back to the question I asked earlier, where do you draw the line? At what point does an incredibly accurate prediction become something more? I'd really like to hear your answer, not because there's a single correct one, but because the conversation becomes far more interesting once you've seen how the system actually works. Some people will say understanding requires experience. Others will argue that if a system consistently reasons, adapts, and solves new problems, perhaps our definition of understanding needs to evolve. Both perspectives raise difficult questions, and that's exactly why this topic matters. But there's one conclusion we can reach with confidence. The question in this video's title quietly changed while we were answering it. We asked, what does AI actually think in? The evidence points somewhere slightly different. AI doesn't think in English, it doesn't think in images, it doesn't think the way people do. What it builds is a mathematical landscape where meaning emerges from structure. Every concept gains meaning because of its position relative to countless others. Move enough of those relationships into the right place, and behavior begins to look astonishingly intelligent. That's the idea that changed artificial intelligence, and it might eventually change the way we think about intelligence itself. Because maybe the biggest surprise wasn't discovering how AI works. Maybe it was discovering that our own intuition about thinking was incomplete. The next time you ask an AI a question, you'll probably picture something very different happening beneath the surface. Not a machine searching for an answer, a landscape coming to life. If you enjoy exploring ideas that seem obvious until you look closely enough, subscribe and join me for the next one. Every episode on this channel starts with a simple question and ends somewhere neither of us expected.